So welcome to the second seminar in the PAGES2k Network Online Seminar Series, which will run regularly through this year, 2021. And so we started these seminars to showcase the activities of the network over the past several years, but also present current research activities and also highlighting promising areas for future research. My name, as you can see in the screen, is Hans Linderholm, and I'm one of the 2K coordinators. And today I have the great pleasure to welcome Raphael Neukom to give a talk here in this seminar, which is, as you can see, going to be about temperature reconstructions from the PAGES2k Consortium. Very exciting, and just before Rafi starts, I would just like to introduce him to you all. So Rafi is a paleoclimate scientist, and well, most of his work has been focused on quantifying regional to global climate over the Common Era, the last 2,000 years. And he was involved in the PAGES2k project already from the beginning. And during his PhD, he was working on South American paleoclimate and has written some really good works about that. For his postdoc, he collected more data, reconstruction, and made data model comparisons from the Southern Hemisphere continents, which you may have seen likely. And Rafi has been involved in many of the consortium-wide PAGES2k activities, including these global reconstruction efforts, which he will talk about. He was, of course, also a coordinator of PAGES2k for some time, but during the past couple of years, he has been working on future climate risks in Switzerland at the Universities of Freiburg and Zurich. So we're really happy to have Rafi here. There's bound to be lots of questions in connection to the talk. So if you have anything, you can post your questions in the chat. And I've seen that people use that to say hello, which is nice. You can also post questions there. And after Rafi's talk, we will have a question and answer session. So unless there's any immediate questions, please, Rafi, go ahead.
Thanks a lot, Hans. I hope everyone can hear me and see my screen. Yeah, thanks for the introduction, and thanks for giving me the chance to talk here in this PAGES2k seminar, and welcome everyone. Great to see so many familiar names and faces. As Hans has said, I've moved away a little bit from the 2K science, so it's great to see you again, and already apologies if I have missed some of the most important progress over the last 2 years or so, then you can remind me in the end. So what I'm going to present today is not so much only my work, but a lot of work from many members of the 2K Consortium that have contributed to all these efforts. An alternative title for what I'm going to talk about today would be Can a Larger Hockey Team Together? Yeah, it's still somehow about the hockey stick. We cannot get rid of it. And yeah, it will come up also during my talk. Fortunately, the Team Canada has just made it to the quarterfinals of the Hockey World Cup yesterday, so I didn't have to change this image. Let's see how they do in the future. And let's see how the reconstruction hockey team can do. And as I show here, that's the news from one of the largest newspapers in Switzerland when our reconstructions were published. The headline was Bern widerlegt Argument from Klimaskeptiker, which means University of Bern disproves argument of climate skeptics. So that's still the main headline, and not something like climate models do a good job or strong climate trends or whatever. So it's still about climate skeptics or denialists being wrong, which you all know already for a long time. But anyhow, that's a situation we are facing. And maybe to start with, the hockey stick that was from the last IPCC report. You all know this figure probably very well. So hemispheric temperatures, Northern Hemisphere, last 2,000 years. Many spaghettis from different reconstructions. And we really don't know where the differences among these reconstructions, which are quite strong in some periods, actually come from. Is it just because of the data, or is it also because of the methods? And yeah, one of the aim of the reconstructions that I'm showing here is to really also get an idea of where such differences may come from. So I'm going to start a little bit with the process of these reconstructions, also a bit about the 2K effort that's behind it. So for all these who are not so familiar how PAGES2k projects work, maybe some insights. And then briefly about the reconstructions, what they show and how we interpreted them. And then I hope I have time to also mention one or two challenges that we faced during this PAGES2k project. So I'll start with this figure here, or this paper. So that's probably, you all know, it is the 2013 Nature Geoscience paper from the PAGES2k Consortium. So the first larger PAGES2k Consortium paper, which presented regional continental scale temperature reconstructions. It was a huge effort by Heinz Wanner and Daryl Kaufman and others to bring this all together, and it ended up in a nice paper, obviously. And the disadvantage is that this paper is still being used until today, or cited very often as global temperatures, although that has not at all been the purpose, and it shouldn't be used because it's a obviously regional temperature reconstruction, but it's still almost every week I see citations of this paper for global temperatures. So we should change this. That was one of the plans. And then the next logical step was this data description paper that probably you all know as well. So the data collection of global temperature proxies over the last 2,000 years. Again, a big effort led by Julien Léger and others to bring this all together in a really nice format. So go check it out. Also on the website, it has data are available in different formats, really ready to use for any reconstruction effort. And so it basically, the database ended up with almost 700 records from all over the globe, being somehow related to temperature. And that's basically a perfect starting point for doing such global reconstruction. So calls for contribution to global with this 2K, not familiar with it, it's almost always like bottom-up approach. So some people have a good idea and suggest it, and if many people think it's a good idea, then it's being opened, and on the PAGES newsletter and website you can see it and join if you're interested. And that was the same thing in 2015 here for this project. One initiative was doing temperature field reconstruction, so reconstructing the whole globe, gridded globe, and the other one was doing a reconstruction for the global mean. These are actually two individual independent projects, and for the field reconstructions there were not so many volunteers, so we ended up being just 5 people. No senior scientists, just young people who tried to do some good work together, a really constructive effort in the end, and a lot of fun. And for the global mean temperature, we had much more interest and more people contributing, which led to more wider discussions and a kind of different group effort. At the beginning, no one really had time to lead this effort, and in the end, I took over there as well. But really, the two efforts are independent, and also people joined later on. So if you see an interesting PAGES2k project on the website, maybe don't hesitate to ask. Very often, contributions are very welcome. So in the end, it ended up in 2 different papers that were in the end published at the same day. And I'm going to talk now a little bit about the work behind that. So behind that, So the aim was really to do consistent reconstructions with more than just 1 or 2 methods. So we built 5 by 5 degree temperatures over the globe. And for all of these efforts, we used the same reconstruction period, so 2000 years, common era, annual, April to March seasonal window. And in the end, we had ensemble reconstructions for all methods that we used, so at least 100 members for spatial reconstructions and 1,000 for the global mean reconstructions to allow also kind of probabilistic analysis of our reconstructions. And most importantly, really consistent other reconstruction parameter as far as possible, so same calibration periods, same input data, to be able to really compare the results in the end and know where the differences potentially come from. Briefly on the data that we use for reconstruction. So obviously, as you see, we started with this PAGES2k database from 2017, but then we only really used a subset of those for our reconstructions. First of all, we used those that passed a little bit more stringent screening, which is called the false discovery rate screening. You can read about this in the database paper. So only selecting those records that really have a significant local to regional temperature relationship. That reduces the database to 257 records, and then we only used those that have annual data or at least one value per year, and also cover the calibration, the instrumental calibration period, because most of our reconstruction methods still need this as a requirement to actually work. So in the end, we had 210 records, which is still a nice number to work with. But if you look at them over space and time, obviously, we see some unequal distributions. You probably all know this problem. Our database is biased towards Northern Hemisphere tree rings and tropical corals. And on many other regions, we still have data deserts, let's say. The Africa or the Southern Ocean is basically like long-term data, which obviously complicates the whole situation. And in time, we have the same situation. Just the number of available records over time, you can see that most of the records just cover 400, 500, 600 years, and in the first millennium we have like a handful or 2,000 or so of records that cover the full 2,000 years. So we need to be careful with interpreting any results prior to, let's say, the year 1000 or so. But that's what we have, and that's what we take. And so I'll now first report about our results from the global mean reconstructions, and then a little bit about the spatial reconstruction results. So reconstruction methods, I could talk a lot about this, but I think that's not so interesting to go into all the details here. I've listed all the methods that we use to reconstruct global mean temperature here, subjectively sorted from the most simple method at the top to the most advanced method at the bottom. You probably have heard of all these methods. They have been used a lot, particularly the top ones, composite plus scale, principal component relation, RegEM, that has been used widely in the past. And then we have some more advanced methods like pairwise comparison, which can also do nonlinear analysis, also Bayesian statistics here used in one of the methods, and data assimilation, which also includes information from climate models, by Kalman filter and proxy forward model approaches. So all these methods, same parameters, and then you end up with these reconstructions over the last 2,000 years. That's a 30-year filtered ensemble medians with different colors for the different methods, and the ensemble range in gray. And I'm not going to talk a lot about the temperature history. You can see the significant negative temperature trend, linear trend over the pre-industrial common era, followed by the strong warming, obviously. And what's interesting, I think, is to see the agreement or disagreement among the methods. So in general, I think the agreement is quite good, but you can see that we still have problems in the low frequency. So much stronger little ice age cooling here for this Bayesian hierarchical method, models method, or stronger warming here for the RegEM method at the very beginning of the common era. So the low frequency is still a challenge, and that's no surprise given that our high resolution records that we use are not, as we know, not very strong in capturing the lowest frequencies. So we also looked at other frequency bands, and I want to show here the multi-decadal scale. So that's filtered 30 to 200 years, so the multi-decadal to centennial time scales. That's where I think the reconstruction are most reliable, not only because of the data, and also because of the agreement. You see that here, if you look at this band pass at multi-decadal scales, the agreement between the methods, the different colored lines here, becomes really remarkable, I think. So that's quite a good agreement. And that's maybe also already one of the answers to that spaghetti plot that I've shown at the beginning. On the multi-decadal time scales, the method really doesn't matter a lot. So you can use whatever reconstruction method you want, almost, I would say, and you get a very consistent results. So this, if you get differences in that domain, it's probably mostly because of different data selections. We have also compared a little bit our results with another data set, for example, on-screen full database, and this still looks quite similar. Now here I compare the reconstructions with models, CIMI 5 past 1000 models, 23 simulations, that's shown in gray here. And for me, the most striking thing probably of the whole experiments that we do was this really good agreement between the data and the models here between 1300 and 1800. That was quite striking to me. In terms of the magnitude and also timing of the fluctuations, that's quite a good match, I think. And that shows us that obviously if you look at multi-model, that's in the end a representation of external forcing, and that matches quite well to our reconstruction. So that shows us already that we see external forcing in our results, and that's also evident looking at volcanic eruptions here, for example, in green. But that also shows the periods where we have a little bit of disagreement, beginning of the 19th century, obviously, and after Samaras, where the models still see a stronger cooling than our data. And the instance here where the eruption was not yet implemented in the forcing for the model simulations, where reconstructions show a cooling. Another thing that we were interested in was not only the temperature history, but the rates of warming. So how fast is it warming or cooling at multi-decadal time scales. And this figure here shows the 51-year warming rates, velocity of warming, linear warming trend over the past 2000 years. Whenever it's red, it means that the Earth is warming, and when it's blue, it's cooling, and the higher the values on the y-axis, it means that it's a faster warming. And not so much surprising, we have the strongest warming in the 20th century, and towards present, it's really about 3 times warmer than any time in the pre-industrial era. But again, what I think is maybe most remarkable here is the 2 horizontal lines here. The green one is from the reconstructions, the orange dot one is from the climate models, and it shows the upper range of pre-industrial variability represented by the 97th percentile of climate models and all reconstruction ensemble members, and that agrees really on spot. So that gives us some confidence that the models confidently also interpret the magnitude of warming in the pre-industrial times, similarly as you see it from the reconstructions. So again, good news. And one of the questions we can ask here is also, where does warming in pre-industrial times, or the fastest warming, come from? When does the Earth, when did it warm in pre-industrial times? Relatively rapidly. And again, it's very enlightening to show the volcanic eruption here with some green triangles. And we see not only the strongest cooling events happened after volcanic eruptions, but also each very strong warming is almost exclusively related to a cooling. So we can basically say when the Earth warmed in pre-industrial period, it was always a response or a recovery from cooling after a volcanic eruption. So strong warming in the past 2000 years only occurred after volcanic cooling. In contrast, obviously, to the present day warming. That's also quite enlightening, I think. Yeah, so much for the global mean. Let's move to climate field reconstructions and the questions we want to solve there. First, very shortly, briefly again for the methods. We used 6 methods there. 3 of them that are shown here are the same that we used as we used for the global mean, just implemented differently so that it can deal with fields. So from very simple point by point index regression that were then pasted together into a field, again to more advanced methods. And we use 3 additional methods that are really specifically designed for fields. So 4 purely regression-based statistical methods, and then we have 2 methods that also implement information from climate models. Basically, or very simply spoken, the temporal information is taken for the proxies and the spatial information from the climate models. So the proxy information basically translated into a physically consistent field, or at least what the model thinks is physically consistent. So that allows us again to compare these different reconstruction method. And again, the agreement is quite well. I do not show reconstruction results in detail for one region or so, but I directly move to the questions that we really wanted to ask in this work, which is like, how consistent was warming or cooling in a different period, or more precisely, did the peak cooling or warming in the Little Ice Age or Roman warm period occur at the same time everywhere? Or was the coldest period of the Little Ice Age occurring at different times in different places? How do you look at this? Let's first again look at the temperature history of the last 2,000 years and split it up in different periods. So Little Ice Age typically used between 1400 and 1850. Okay, at each location, when was the strongest or the peak cooling at the different places? For that, we take a little bit wider search radius and say, okay, we search for the coldest 51-year period at each location within the last millennium. And then we do the same for the medieval climate anomaly, search for the warmest 51-year period at each location in each ensemble member between 750 and 1350. We search for the coldest 51-year period in the first millennium, and that would be our Dark Ages cold period. And similarly, we do for the Roman war period. And last but not least, we want to know when was the warmest 51-year period over the entire 2,000-year period, which you then potentially can call the modern warm period, depending on the result. So just an example, we take a grid cell, for example, Central Europe or Vienna in this case. Take each reconstruction ensemble member. We have 600 of them. I show 6 as an example here. And for example, the cyan line here has its minimum, so that's 51-year averages, and that one happens in 1834 for another member. At the same year, for another member, for another method, again at the same year, other members maybe in 1841, 1884, 1840. So for each member, we identify the coldest 51-year period, and that ends in a PDF of the ensemble probability that the coldest 51-year period occurs at a certain time, and we interpret the maximum of this distribution as the most likely coldest period in Vienna. In this case, 1840, and we do that for each location over the globe, 55 to 5 degrees, and then we can answer the question, which century contained this coldest 50-year period at the individual places? As you can see here, it's for many places in the Earth that's in the 19th century, but it's also earlier, for example, in Northwestern Europe or Eastern North America, and it can even be in the 14th century as in large fractions of the Pacific domain. So we interpret this that the peak cooling is really not spatially consistent. And we can open that to all the other epochs of the last 2,000 years, Dark Ages, cold period, Roman warm period, medieval climate anomaly, and still we see that it's not consistent. So the cold and warm peaks are not in the same time everywhere. The one exception is the really warmest 51-year period over the full 2,000 years, and that's consistently happening over the last century, in the 20th century, except for a few regions here in Antarctica where the data situation is problematic. So we have consistent warming really only in the last 100 years. What's the cause? Briefly, we also tried to look at explaining a little bit what's causing the warm and cold periods. that we reconstruct. We mainly did that for the global mean. We also tried for the field, but that's a bit more complicated. So I'll report on our detection distribution experiment for the global mean. I've stolen the slides from Mike. Thank you, Mike. A nice explanation of how that works. Just briefly, typically we use regressions from simulations that are fully forced, so solar, volcanic, and greenhouse gas forcing, as shown here, and regress that with our temperature reconstructions. And that gives us a slope, which we call then the scaling factor. And if the slope is 1, we basically say we have a, or it's clear that you have a good agreement between these forced simulations and our reconstructions. And so that's giving us a consistent temperature history by the forcing and the reconstructions. And we say we can explain our reconstruction variability by that forcing fingerprint from the model. And nicely also, the residuals from such a regression can then be interpreted as the magnitude of the internal climate variability. And we can repeat this exercise by using model data that are only forced by greenhouse gas simulations, or only forced by volcanic forcing, or only forced by solar forcing here with the different colors. And then we can see how strongly each individual forcing is influencing our temperature history that we have reconstructed. And the results in our case are shown here. Left for the total forcing, so fully forced, and the box plot is for the whole reconstruction ensemble, and the different colors circle are different reconstruction methods. And you can see we have a scaling factor, excuse me, of almost 1. So really good agreement here, and we can say that external forcing is really having an influence on our reconstruction because it's significantly above 0. If you look at the individual forcings, the story is a bit different here. You can see that solar forcing, our scaling factors encompass the value of 0, which means that we do not see a significant influence of that forcing on our reconstructions. And I'm still talking about decadal-scale reconstructions, or multi-decadal scale, excuse me, and pre-industrial, so that's between 1300 and 1800. In contrast to solar, we can see that volcanic and greenhouse gas forcing are significantly above 0, and particularly volcanic forcing is very close to 1. So that's, as other people have also identified this recently, volcanic forcing seems really to be the driver of our variability in the past 1,000 years at least. Now, the good thing is that we can now look at the residual, as I said, from the D&A experiment, and that gives us an estimate of internal climate system variability, and we can compare that, for example, to model control runs, which are unforced. And the magnitude or the variance here is quite comparable, as you see. So they are within each other's uncertainty range. It gives us some confidence that the multi-decadal unforced variability is in this order of magnitude. We also looked at the medieval quiet period, which was between about 1850 and 1100. Quiet means little variability in solar forcing and very little volcanic eruptions. So we can call it almost an unforced period. And during this period, you see the variance of the models here at the right and the reconstructions at the left agree quite well, which is another indication that actually our models capture the unforced natural climate variability quite well, which is also great for our confidence in these models to predict the magnitude of decadal variability superimposed to future climate mean warming, which is good news. So much for our key results. Maybe briefly on one of the key challenges that we faced in our reconstruction process as the last thing. Can we do better than just using pure noise data in our reconstructions? I think that's one of the questions we should all ask ourselves if we do temperature reconstructions. And often we forget about doing this, but I think it's very important. Just one example here, that's a reconstruction using global mean reconstruction, just using pure noise proxies that really have the same autoregressive structure as our real proxies. And you can see we get a really nice hockey stick out of these just noisy data. So just because we have this strong temperature trend in our calibration or instrumental overlap period, any predictor data that has a similar trend or just a strong autocorrelation as well can be easily calibrated. And if we just calculate reconstruction skill for this noisy data set here, we can get easily a very significant climate reconstruction or temperature reconstruction. So for temperature, I have these strong trends. We need to be careful and not just report a high skill, but we also have probably to also look at different robustness measurements. For example, comparing our results to noise proxies. So if you do better than that, at least we have some indication that it's not just rubbish what you reconstruct, let's say, extremely spoken. That's an example from an earlier reconstruction from the Southern Hemisphere. We chose 4 different reconstruction skill measures, root mean square error, and 3 different variant types of RE, reduction of error, reconstruction skill. And the red shading here is just a lot of pure noise proxy reconstructions. The red line is the median, and black is our real proxies. And you can see with pure noise proxies, it's really easy to get a skillful reconstruction, at least 400 years back or even further, depending on the measurement that you take on the skill measure. So the challenge is really to be better than the noise data. And in this case here, it was actually the case. So almost all of our real proxy reconstructions, or for most measurements, we are outside the 95% or even 100% values from the noise proxies. So we have some confidence that the reconstruction is almost, or is a little bit robust at least. And not only for the skill of the reconstructions, but also for the interpretations, we should take a little bit of care whether our results are maybe just occurring from screening or calibration or so, or whether they are really robust. So just the example from our trend analysis for the global mean, where we reported highest trends over the last 100 years. Here I showed, as a function of the trend length on the x-axis, I show the ensemble probability that the largest trend really occurs in the industrial era. And you can see in black with our reconstructions, the largest trend occurs in the industrial era with the large ensemble probability of at least 50%, let's say, for trends of 60 years and longer. Now, if you take just pure noise data, obviously, it's, as I said, it's relatively easy to get a trend out of it in the 20th century. And so if we reproduce the whole thing with noise proxies, we get the orange line. And so even with noise proxies, we can still get the high probability that the fastest forming occurs in the 20th century. But it's clearly different from our real-world reconstructions. And so we can say we have a big difference, so we're confident that it's really not just noise, what we did here, but we're doing a little bit better. And together with other robustness tests, I think that's quite helpful. Maybe just briefly in the global field reconstruction exercise, almost all of the review round process that we had, 3 rounds of review, was just because of this very issue. How can you be sure that the spatial consistency in the 20th century is not an artifact of calibration and proxy data screening? And so 3 rounds of review only to answer these questions. And we had to do noise proxy experiments. I'll keep it short now. And we really had lots of discussions with the reviewer, which is the correct amount and type of noise to use. And only after we did 54,000 reconstructions of pure noise, which took about 100 days of calculation time on the high performance computer cluster in the University of Bern, we could show to the reviewer that the spatial consistency in our real proxy experiment is just higher than whatever noise proxy experiment you do with different methods, different screening methods, different reconstruction methods. It's just whatever we did, the real proxies showed a larger consistency of 20th century warming, and only that convinced the reviewer that it's not an artifact. And in the end, I'm grateful to the reviewer because, that gave us really some confidence that the result is really robust. And so I think for all kind of reconstruction experiments, we should take care of this. So in the end, the reviewer was happy. And we were exhausted, and you're probably also exhausted now because I've been talking already too much. So to sum up, we have the fastest forming rate over industrial era, and that was over the last 2,000 years, and that was above natural variability. Warm and cold peaks in pre-industrial times did not occur globally synchronous, in contrast to current warming, which does. And fortunately, reconstructions are robust to underlying method on the multi-decadal timescales. And to summarize, our interpretations, the data and the models agree on forced and unforced variability quite nicely on multi-decadal timescales. Volcanoes are the key drivers of blast fluctuations and strong trends. Solar forcing is not. And robustness of temperature reconstruction should probably be assessed using some noise or also pseudo proxy experiment, let's say, to be sure it's robust and not only formally skillful. That's it. Thanks a lot for your attention, and I hope we can have some discussion about this now.
Thank you very much, Rafi, for a really interesting presentation. I will open up. There's been quite a activity in the chat, and I'm not really sure. Would there be any comments based on this? Mike has a question regarding slide 40, if that figure made it to the paper supplement.
Slide, this one? Oh yeah, that's in the it's called extended data figures. So about 50% of the supplement is this noise and robustness experiments that we had to do. Yeah. You can read it there, or can try to explain it a bit better if you're interested.
Okay, so do we have any more questions? And I think that there's quite a big crowd, so I think that if you just unmute and raise your voice if you have a question, I think that would work better than me trying to go through all the participants. So any questions for Rafi regarding his talk?
So I was wondering about the variability estimates. So is there still the issue that you're underestimating variability? So basically that you're biased towards reducing variability in your reconstructions? I mean, did you try to do some pseudo experiments here? Because I'm a bit surprised that models and data matching is so good. I would expect that the reconstructions would basically have a lower variability because you tend to damp your variability here.
Yes, that's correct. So I was also surprised a bit that it matches so well in general, also on the multi-decadal time scale, but I still think, yeah, we're underestimating this, particularly if you go further back in the first millennium AD. Some people have shown with tree rings more recently that we are, for example, for the eruptions, strong eruptions in the 6th century, we're not really matching the variability there. So still room for improvement. But I must also say, we're not doing so much worse than some of the pure tree ring reconstructions that have been shown recently. We can still improve,
but if you try, if things are consistent, so basically you use the model and then simulate from the model, noise approximate, and then reconstruct the variability again, will you then get lower, or will you be somehow, will it be consistent? I mean, if you take, because if you then get would get out, let's say, half the variability, but you're still fitting, that this means that basically there is an inconsistency. So you could do inconsistency check by simulating pseudo proxies with the model and then seeing if you still get the same.
Yeah, that's correct. So we did some of those such pseudo proxy experiments also as a side project, and I think at those timescales it doesn't look too bad. But I'm not 1% sure whether that would be really the case. So that would be interesting to do.
Thanks. Yeah.
Okay, so we have some hands in the air, but I'd like to cut in with a question from Natalie. So what about precipitation reconstruction for the last 2K?
Yeah, I'm probably not the best person to answer this question. So there has been efforts to do that, particularly using now data assimilation methods. And I think they're pretty good over some areas, but over data sparse areas, yeah, it's clear it's even more difficult to do that. But you have a look at Nathan Steiger's paleohydroclimate reconstruction. It's available, and I think even some newer efforts. I'm sorry if I'm not fully up to date, but some data are available. Although it's obviously much more tricky to do. PAGES2k, yeah.
Yeah.
Says Mike, obviously.
So Paul raised his hand. Paul Butler.
Oh, hello. Can you hear me?
Yep.
Yeah. Hi, Raphael. Thanks for that. That's a great talk. I also put this question into the chat. You had a slide on the rates of warming, didn't you? And
Yes.
it showed some kind of upper limit on those, which was higher than any actual rate of warming in the pre-industrial. Am I reading this graph wrong?
Yeah. So I go back to that. In the meanwhile, check Jason's answer to the last question and my statement about PDSI versus precipitation reconstruction. He was correcting me there. He's obviously quite right. So the warming rates. Yeah, so the upper range here is across the entire ensemble. So the 97.5 percentile, whereas the line is just the ensemble mean of the warming rate. So there is obviously an uncertainty range about this single line here. Mm-hmm. And I just didn't show it here. You can see it in the paper, the uncertainty range is in the paper.
Okay.
Include the uncertainty from all, or just the ensemble range, then you will get that that line.
So is the reason it's high because it includes the modern warming? The modern is the reason it's so high that the what presumably is the central line is so high that it somehow includes the modern rate of warming?
No, it's only pre-industrial.
Only pre-industrial. Okay.
Yeah.
Okay.
Yeah.
Thanks.
Okay, there's lots of questions and comments in the chat, but there's some questions regarding mixing proxies with different seasonal targets, and if you can actually extract different seasons from the data set, and if it creates some bias when you have, for instance, many of the tree ring proxies are summer targets and so on.
Yes, obviously. So yeah, that's very clear. I mean, we're almost all proxies are seasonally biased, and as you said, the big bunch of the data set comes from the northern hemisphere and is biased towards the summer there. So obviously that's a clear bias that we have. That's, yeah, we need to be very clear about this. We have a seasonal bias. We have an also spatial bias, because just the data are not evenly distributed in space, time, and seasonality. So it's interesting to compare that with other reconstructions that focus on individual seasons or just take different archive subsets. But that's a very good point. Yeah.
All right. I think Rob raised his hand. So Rob, you want to ask a question?
I was busy writing my question out.
Yeah.
Actually, I'm kind of, this is not really to Rafi, this is to the community, but it's responding to Mike. I think he said earlier about what next for PAGES2k. And I wonder if PAGES, and that's all of you with that PAGES hat on, have influence on the funding councils, because clearly we really need to now shift focus to the first millennium AD, right? And it is actually very difficult for the data generating community to get funding for, I guess, individual locations, right? You've got a network, but that's built upon years and years of people's individually working or maybe some collaborative stuff. But now really we got to think of this as a global collaborative project, which PAGES has been doing, but PAGES hasn't been funding data generation. It's been utilizing whatever data is there, right? And surely the next step is to somehow influence the funding councils to, I guess we don't really need to focus on the last millennium so much, maybe in the Southern Hemisphere, but in the Northern Hemisphere, yeah, we've got what, 9 long tree ring records that have some degree of temperature, it's not a lot, right? So it's clearly that it's going to be noisy. Clearly, we're not probably going to get the full spectrum for climate variability. So this is not really directed at Rafi. This is directed at those people in this virtual room. You know, what is the next step to influence the funding councils? Or do we just now focus on mitigation? It's warming. We're kind of fucked. I mean, we've got to do something about it now and just forget about paleo. Pardon my French. That's my question. No simple answer, I know.
Probably someone from the 2K coordinators can answer it better than me. I would just say that I agree a lot that we have to really focus on the data much more. Well, methods are important, but we see they agree quite well. But getting the data coverage better is really the crucial thing if you want to improve our reconstructions. I fully agree with Rob and all the other data generators that they should have a chance to get reasonable funding.
Yeah, just before I let Raphael in, I just want to remind you that next week there's a town hall, PAGES2k town hall meeting, where the potential future of 2K will be discussed. So, I mean, there's clearly lots of interesting ideas coming up here. So please join, and in the chat, there's a link and there will be information everywhere. Raphael, you want to say something, please?
Yes, thanks for the talk. I was wondering, so that, yeah, it's remarkable, this great agreement that multi-decadal timescales and variability, but then, so I guess then the problem is more at centennial timescale, that then the reconstruction methods don't really agree. So I guess if you bandpass the filter over that timescale, then you would get very different trends from the different methods. And that seems counterintuitive, right? Because we would imagine that on the longer timescales, the noise average out and we get the same trend. So I was wondering if you have any ideas why the different methods don't agree on the longer timescales, but they agree on the shorter timescales. Maybe it's related to the tree rings, which have the low frequency issue, but I guess that's something that has been addressed. So yeah, that's the question. Thank you.
Thanks, Raphael. Yeah, I mean, partly it's certainly because or clearly also because of the data, because yeah, we have little data that have really a reliable low frequency signal, and so depending on how you weigh them in, your results may get different. And I must say that some of the methods used were able to use low frequency data and others are not, and that's why the differences come from. So we're still having troubles with somehow calibrating records that have no or one or two data points in the 20th century. I think that was also one of the questions. Some methods can deal with that, but most of the others can't. And it's also obviously difficult to then validate this thing. So getting methods that can deal with the low frequency calibration and getting records that have it right and getting a critical amount of data that have it right, because currently, as also Rob said, it's very little data that have this low frequency reliably in there.
All right. Jason, you've been waving your hand for a while, please.
Hi, can you hear me?
Yeah.
I just wanted to respond to Rob's comment. I was typing it in the chat, but I'll say it in voice. Rob, I think the critical, even if you accept the fact that adaptation is should be our focus, which I know has been part of the discussion. Adam Sobel had a opinion piece on that recently. But if you accept that adaptation should be our only focus, a critical piece of that is reliable and accurate predictions and projections, which of course are tied to the models. And assessing the models is something that the paleo community has to continue to double down on and recognize as an important area that we can contribute to. And in particular, high-res paleo over the last several thousand years can target what I think is one of the most critical aspects, which is extreme events. So paleo has the capacity to provide more sampling and more assessment of extreme events. And I think a critical question for the models is whether or not they can reproduce and accurately estimate the nature of those extreme events. And so I think it's, even if we accept this adaptation argument, I think paleo has an important role to play in the way that we can help evaluate models and improve the reliability of the projections and predictions that we require for adaptation. So I wouldn't throw the baby out with the bathwater.
Oh no, I fully agree with you. I was just sort of, putting it out there.
Yeah, but I guess we have to be careful about accepting your premise. I mean, the idea that paleo doesn't have, particularly high-res paleo doesn't have a critical role to play in model assessment is something that we need to continue to beat as a drum, I think.
Yeah. Good. There's still lots and lots and lots of comments and questions here. JC, you had some specific question regarding the paper. Was it something you want to continue with, or?
I don't want to monopolize time, but I guess the point I wanted to make with regard to the work that Rafi presented is that it really is the first large-scale CFR comparison with a consistent, in other words, the same input proxy data. That's been done a lot on pseudo proxy experiments, but I think there's a lot more to dig into regarding the methodological differences. That's been brought up by other people here, but it's a real, I think, treasure trove of data for looking at how these methods perform using the same input data. And there's already, in looking over the paper, Rafi's paper, for instance, the analog method seems to perform better in terms of its field skill than a lot of the other methods. And that's an interesting thing to me to understand. But just more generally, I hope that there are more plans to investigate the methodological behavior given this really nicely constructed common protocol for all of the same input data measured, processed through a wide range of CFR methods.
Yes, I would agree, Jason. And it's true that if you look at the temperature history from these different methods, there are some quite striking differences sometimes, which we didn't have time to look at and really don't understand. And so, as soon as you go into space, in some places, obviously, the method starts you start to really see these differences. And so, getting other methods in or just comparing those a bit more, I agree, would be really interesting.
Great. So do we have any more questions or comments? So if you feel that your question has not been answered, that you posted in the chat, maybe you can just ask it now. And just to remind you again that next week on the 9th of June, there will be these town halls where the idea is to discuss potential future directions of 2K research, what would be interesting topics, and we've heard about hydroclimate here and lots of interesting stuff. So there's one meeting at 7 o'clock in the morning UTC and one at 5 o'clock in the afternoon UTC. Well, unless, yes, of course, and there's on the 16th of June there will be Michael Siegel, who will give another presentation. So lots of things happening. So unless there's more questions, I would like to thank Rafi for a really great talk. I would like to thank all the participants for good discussions and an active chat. So actually over 100 people have been in this Zoom meeting. So thank you everyone, and especially Rafi, thank you very much. And we hope to see you at the other upcoming seminars and also at the town hall. So thank you very much.